Okay, so some brief introductions. I am Hayes Cozart. My background is that I have a Bachelor's of Science in Psychology and worked as a pricing and data analyst in telecommunications. Kyle, who was not able to make it today, he had a Bachelor's of Science in computer programming and had a background heavy in computer engineering, just to give you an idea of what our team is like.
And my name is Arda. I studied mechatronics engineering as a bachelor's in Istanbul. And then I received my MBA. I worked 2 years as a sales and application engineer in a maintenance company. Then I moved here and I started my transition to data science, and that's why I'm here today. So our Capstone project is about Grupo Bimbo. As Chris mentioned, it's a Mexican bread production company, and it's an ongoing Kaggle competition. So as a start, I'll just briefly introduce global baking industry and Grupo Bimbo, because when we were starting the project, I have never heard of Grupo Bimbo before. So for the people who also never heard, so the global baking industry is a $461 billion industry, and bread, as you can see in the top right, bread is the largest segment with 53%, and its expected annual growth rate for the next 5 years is 3%. It's a really competitive market. There are 277,000 companies operating, and those are like small bakeries, regional family-owned bakeries, supermarkets, and grocery store with in-store bakeries. The four major players are Grupo Bimbo, Mondelez International, Yamazaki Baking Company, and the Kellogg Company. And those four account for the 10% of market share. And strangely, Grupo Bimbo is the highest that we have never heard of them, with 4%. So Grupo Bimbo has over 1 million stores and 45,000 routes in New Mexico, and its annual sales is $14.1 billion, and its operations in 22 countries. So it's a growing market, and it's important for them to meet the demands of their customers. So their current inventory calculations are performed by their direct delivery sales employees and based on their experiences in each store. So they are manually predicting it. And they have like really products which have a shelf life of 1 week. So it's really, the error margin is too small. So our problem is developing a model to accurately forecast inventory demand based on historical sales data. We have 5 data sets provided by Kaggle. Our training set is about 3 gigs and 74 million observations, which didn't make job easier. Our test set has 7 million observations. We have also extra CSVs for client names, product names, and town and state information.
Okay. So to give you an even further look into exactly the data that we had in the train set, basically, if you understand Spanish, then these variables actually make sense. But if you don't understand Spanish, we had week, the sales depot, the channel, the route, the client ID, the product ID, how many sales they had in units, what their sales were in pesos, what their returns were in units, and what their returns were in pesos. And then what we were trying to predict, demand. So in front of you is a correlation plot, and all of the top, 6 variables, those are all categorical. So the correlations are interesting because keeping the categorical variables as numeric actually helped our predictions, which means that there is a pattern to the IDs, or most likely a pattern to the IDs. And also, obviously, sales is highly correlated with demand because what demand is sales minus returns. So that's a brief overlook of that. Here is a scatter plot of all the numeric variables, and then also their distributions. The important thing, like high topic notes to take from this is, as we can see, demand and sales are basically the same because the only difference is whenever there was returns, which if we look at the distributions, the majority of the returns were 0. So only a few times were there actually returns for clients and their products. And this makes it somewhat difficult to predict demand for a simple fact that when we look at demand, most of the demand for a product client, product for each client, is somewhere from 0 to 5 products. That's where the majority of all the demand lies. But it can go all the way up to, I'm pretty sure, 3,000? Yeah. So the demand can be 3,000. So there's a lot of variance in the actual data set. And the standard deviation is about 25 for the demand. So this is why this is a rather difficult thing, is there are very few returns, but those are very important to the demand. So now if we look at product ID and adjusted demand by week, we actually can see some patterns. Why this is important is that actually every 4 weeks, the patterns look a bit more similar. Like you can see that they basically have the same sort of trends of what product IDs and what their demand are, but every 4 weeks, they look much more similar to each other. So week 3 looks much more similar to week 7, and week 4 looks much more similar to week 8. Why this is important is, based on our data, the test weeks are week 10 and week 11. So the weeks that would be most similar are week 7 and week 6. And week 6 is the most different from all the other weeks. We think this is the case, but we don't necessarily know this because we don't know what the demand for week 10 and week 11 are. So we tried various models. All of these models are tree-based models. And first, we tried random forest. The problem with random forest is simply computation time and the sheer amount of data that we had. Even when it was decreased to maybe only testing on a week and training on a week, it still would take way too long, to the point of I wasn't sure if it was ever going to finish. So, and that was including trying to decrease trees and increase nodes. So no matter what I did to try and reduce the amount of computational work that was needed, random forest would not run. So we decided that that was probably not the best model. We moved on to gradient boosting. And for this model, we did 100 trees and a learning rate of 0.05. And this took about 6 hours to run. So it wasn't the best, and it also gave not the best predictive value based on what we found with the test set. So we've finally moved to xgBoost, and all 3 of us used xgBoost and concentrated on feature engineering. Why we moved to xgBoost is basically it was very highly predictive, and also we could run it in a few hours. So it was easy to test out all the new features that we were interested in implementing, and also was actually very highly predictive, much more than the previous models. So why xgBoost, and sort of a brief background of what xgBoost is. So it's a very efficient model, and it allows for parallelizing. It combines both linear models and tree learning algorithms. And as it says down here, is an ideal fit for competitions such as Kaggle. And it also gives you feature importance and cross-validation as part of the package. So it's a very useful package and runs very fast and is very predictive. So that's why we ended up using it. All good things. So to give you an idea of the basic cross-validation we did, we did cross-validation of we would train on the other 6 weeks and test on one, and then we would do that for every single week, so that we would test on every single week but train on all the others to build our final model. And also, in order to pick which features we engineered were more predictive than others, we would test out different depths, and we found through these tests that around 25, so from 22 to 27, different features would either have, a depth of 21 was their best score, or a depth of 25 generally. So this is just showing a basic one where most of them do center around a depth of 25. And then if the feature addition gave us a better predictive score than the past prediction, then we considered it as a good feature. So to give you an idea of, this is just how the data works, so the supply chain that is followed by Grupo Bimbo, so everything starts at a sales depot. It goes to a different route. From that route, it goes to different clients, and then that client has the different products. Generally around 6 each week of different kinds of products. So here are the features that Kyle tested. And these 2 tables are examples of the client table and the product table, because we use these to create our features, since all of our features that we could actually use were categorical, as obviously if you're trying to predict demand, you are not given sales or returns for that week. So the first feature that was tried was the weight of a given product. So each product, in the product table, you were able to parse out what its ID was, its brand, its weight, and how many pieces it was. So we tried out weight, and it was found to be a good feature, increased predictivity when we added it. We tried out number of pieces of the product, and that also was found to help prediction. We tried out weight divided by pieces. If weight was NA or pieces was NA, we set weight to 0 and pieces to 1 so that no errors would occur in the math. And that was also found to be predictive. Now, the most important feature that all of us used and tested is the 3 weeks of lag. So what the 3 weeks of lag is it is the median of the prior week's demand. So it's basically taking the 3 weeks for each one. So like if you had week 8, then you would have the lag for weeks 7, 6, and 5. And then it would keep moving down. And it's just taking the median of the demand for that week, for that client-product pair. We also tried 5 weeks of lag, and even though this did very well locally, when just working with the train, when we used it for the test, it actually was much less predictive. And so that means that probably 5 weeks of lag was overfitting to the train, so it was not a good feature, even though we thought it was a really good feature to start. And then the last one was client name. So for each client, we are actually given their names, and we took the top 10 most named clients, because a lot of these clients only appear once or twice, and we wanted to look at the ones that appeared and had the highest frequency. So we took the top 10 that had the highest frequency. And when we added those and dumbified those as features, we found them to be very predictive. So some of the features I tried are the sum of the lag features. So I tried just summing up all the 3 weeks of lag, and that did increase the predictivity. Instead of just summing what the medians are, I tried summing up all prior demand. So the total prior demand for that product client pair for all the previous weeks. And that was very predictive. As you can see here, not in bold, because it wasn't predictive, was mean prior demand. These actually had the exact same value, which mostly makes sense because there's not much of a difference between these overall, the total prior demand. And we also did k-means clustering. So we scaled all of our numeric features that we have designed. So for instance, all of these numeric features. And we did k-means to those numeric features with k equal to 2 through 10. And then added all of those clusters that we scaled from 0 to 1 and took their means and added them as another feature. So the most interesting one that actually gives some of the best predictive value is actually just the count of the client by town. So the town being where the sales depot is located. So just the number of clients that each town has. We are still trying to figure out why this is as good of a feature as it is. As most of these we came up with just trying to figure out, based on the information we had, what features we could generate. And this one is one of the best. So we are trying to figure out exactly what it's latching onto, because mainly what we were trying to do is there's a lot of new clients, no information about them, so we wanted to separate out differences between those new clients so that we could actually predict on them better, since that's most of what our data is. And this one actually does that very well.
So, this is our feature importance graph for the data set that we created all the features, and it's a really nice graph. So, most of the features we created, like 1, 2, 3, this is included. This is we created. This is created by us. This is included. So, and as you can see, town ID and count, which we have less hope, is like in top 5. So, and the k-means didn't perform well, and we actually surprised that product ID and client names also didn't perform better, because we were expecting better results from them. And this is the added feature scalar plot, and we can confirm that our lags compared to demand is like a linear relationship. So it confirms why they are so helpful. And this is just another, we wanted to see how our features perform, and we want to see their distributions. And so for our current model, we did 1 week outbagging. We trained 4 xgBoost models. As Hayes mentioned, we took week 6, 7, 8, trained on week 9, and then predicted on the test set. We did the same for each 4 weeks. We take the average the predictions, and that gave us the rank 44 on the current public leaderboard. And like 2-3 days ago, we take the current top Kaggle stick, and it's doing some smart merging of medians of previous weeks. We are still trying to figure out how that works. But we took it, and its current rank is 102nd. We did a cross-validation of weighted average. We tried weighted averaging these two models, and we did a cross-validation of that. We tried for a bunch of different values, which gave us the our evaluation metric, which is root mean squared log error. And we fit a polynomial curve to find the minimum, to find the local minima, and it gave us 30%. So we took our 70% of our xgBoost model and 30% of the medians, which gave us the rank 29, and our public leaderboard score is 0.46.
So, future steps. Obviously, we want to engineer more features, as we basically just got started in that front, and some of the ideas that we have are the principal component features, clustering monthly, so week 6 clustered with week 10, so because we saw that relationship between every 4 weeks, and also bi-weekly clustering. Another one that we haven't done, though you saw earlier, is the lag of returns, because it allows us to use some of that information that we can't use in the test because it doesn't exist there, but since if we're doing the lag, we will actually have information on it for the test. Obviously, we think we're currently overfitting to the public leaderboard by the fact that we're doing so well with our weighted average. And we want to do some other models, such as neural nets, to do some much more sophisticated ensembling of the different models. And then, obviously, we want to get back to number one on the leaderboard, which we held for about 6 hours on the 9th of June. So